Now that you've been introduced to the second law of thermodynamics, what we could do now is we could use it and we could wield it in the same way that we use the first law of thermodynamics. And so similar to the mass balances and energy balances that you already know about, what we could do is we could articulate the second law of thermodynamics as an entropy balance. And so when I talk about entropy balances, I'm going to use the abbreviation SB. Okay? All right, and so we're first going to talk about entropy balances for closed systems. And so once again, a closed system is a system in which you have no mass crossing the system boundaries. Okay? All right, and similar to the energy balance, we could write the entropy balance for a closed system in two different formats. And so the first format we could write it in is the rate format. Okay? And so what we could do is we could take entropy ds dt and we could write it as the sum, as I of 1 to n, of our dq dt, or in other words our q dot, divided by temperature for the reversible case. Right? And then this is going to be equal to the sum of qi over ti for the irreversible case plus the entropy generated ds dt. Okay? All right, and so, this is written kind of in a similar manner from the energy balance, but it still looks a lot different, especially considering the fact that now we have a middle part of the equation in addition to the left and the right-hand sides. All right? But really, you could kind of just think of it like this, right? So back at the beginning of the course, I talked about how we have balances and they could all be written in the same way, right? Where on the left-hand side we have accumulation, and on the right-hand side we have an input minus output plus generation minus consumption, a creation term. Okay? And so looking at this entropy balance, essentially this ds dt, you could think of this as the accumulation of entropy. And if we jump to the right-hand side, these irreversible heats divided by temperature, this is going to be your input minus output to the system. And then this ds gen dt, this is essentially your generation term. Okay? And so that's all this entropy balance is saying. Accumulation is still equal to input minus output, and in this case, plus generation. Okay? Now, of course, we still have to highlight, we still are now dealing with these different sorts of terms here in the middle. But the way to think about this, to compare the reversible and irreversible case, the way to think about these is your Q reversible divided by Ti. This is just talking about a hypothetical case, or a hypothetical process, not an actual real process. Okay? And the irreversible case here, this is a real process. Okay? And so that's what we're comparing in the entropy balance. And so the entropy balance is a little bit more complicated, but because we're now dealing with comparing the hypothetical process to the real irreversible process, this actually gives us a little bit more flexibility in how we could do our analysis. And we'll see that later on once we actually start working through example problems. Okay? In any case, this was the rate form of the entropy balance. We could also write the entropy balance in terms of a difference form, where instead of a ds dt, we could write a delta S. And so that's going to be equal to the integral, the sum of the integral of some dqi ti for the reversible case plus the sum of dqi ti irreversible, and then also your generation term as well. And for both the rate and the difference form, our sgen could either be positive if you have an irreversible process, it could be equal to 0 for the reversible process, or it could be less than 0 for the physically impossible process. And at least to, make this a little bit more clear, if your sgen is equal to 0, and this goes away, then what you would have is this is equal to that. And so that's why sgen would be sgen equals 0 would be describing the reversible process. Now, as far as these q dot or dq terms, the way you would figure these out, or one way you could figure these out, is you'll either be given them in a problem, or you would have to derive them from the energy balance. Okay? And so in the next video, we're actually going to go through an example problem where we apply the second law of thermodynamics, and we use this entropy balance to help solve a problem.